All right, we are going to wrap up our conversation about sorting. So here is a sequence of integer values. Draw through the steps, and I don't think I used this term on Friday, but the steps of what we would call scatter and gather for bucket and radix sort. So if you remember, bucket sort and radix sort, those are kind of like the ones where I gave you the exams and you maybe made piles based on the letter. Bucket sort, you're first going to take each of these ints and scatter them into buckets based on the thousands digit, and then you perform insertion sort within each of the buckets, of which hopefully those buckets are pretty small. Radix sort, you're going to first scatter into buckets based on the ones digit, and then you gather. And then you scatter based on the tens digit, and then you gather. And then you scatter based on the hundreds digit, and you gather. Until you finally scatter based on the thousands digit, and then when you gather that time, it's in sorted order. Any questions on that like really rapid review of Friday? All right, go ahead, write this out. These are incredibly useful sorting algorithms for you to have and may appear on the final, who knows? So go ahead, let's say take 3 minutes and practice this, and then we'll come discuss. All right, that was a few minutes. Let's talk about how to do these things. So let's start with bucket sort. And remember that on Friday, we technically learned 2 different types of bucket sort. We learned a bucket sort for int values that have a nice small range where we can just use the indices to represent the counts of how many times those ints are appearing. But if that's going to work, then the array that you make in order to be the buckets has to match the values in your collection. And if you look here, these are all pretty large values. So in order to use that type of bucket sort, I would have to make an array that's at least of size 7,625 because that's my largest number. And that seems like a lot of wasted space. So instead of making that type of bucket sort, we're going to use what I'm going to call the more traditional bucket sort that we can technically apply to any type of object. But we still need to create an array that will represent the buckets. How big would we make an array? Like, how many buckets would you sort of instinctually want to start dividing these numbers into? There's not really too many wrong answers to this, or you could do it in a lot of different ways. But how many buckets, how big of an array would you make to bucket this set? We've got how many? 1, 2, 3, 4, 5, 6, 7 numbers. But it's not so much about how many numbers. It's a little bit more about the range of the numbers. So, yeah, who has an idea for me? Happy to chat things through. Yeah.
My initial thought would be 10 buckets for digits from 0 to 9.
Yeah, absolutely. 10 buckets for digits 0 to 9. And frankly, that is a really common approach to pretty much all of bucket sort. Same thing if it was like a string and they were, English characters or something like that. Maybe you make a array of size 26. And you bucket initially based on the first letter. In this case, I'm going to follow that route, and I'm going to make a bucket of size 0 to 9, and I am going to initially bucket these values based on their thousands digit. So what that means is, if you can see, value 7,625 ends up in the bucket 7, along with 7,403, and vice versa. So the first step in bucket sort is to go linearly across your list and just dump everything into these buckets. But now that they're in the buckets, you can tell they're not necessarily in sorted order. Certainly 2,266 should come after 2010. Same thing with the 7,000s bucket. So that's when they're already in buckets. We will loop over the buckets and perform insertion sort. Then they will be in sorted order within the buckets. And then what we do is we gather and we just start at the top of the buckets at index 0, and we just put things back into sorted order, looping through the buckets, like across the buckets and then within the buckets. Kind of like how you had to do with your iterator in that pesky, remember, chained hash map where you had to go across buckets and within buckets to gather the final ordering? That's exactly what's happening here in bucket sort. Does anyone have any questions on how bucket sort works? Then let's make it a little bit less intuitive. A cousin of bucket sort is radix sort. Now remember, radix sort is what we will refer to as a niche sort. It only works on types of data where there is an inherent sorted order that the computer does not need to rely on a compare to method for. So numbers, strings, those are inherently sorted, like the computer understands, alphabetical order and numerical order. So in radix sort, the first thing we're going to do is we're going to scatter into buckets. And we're going to start, instead of in this one where we went based on the thousands digit and then ran insertion sort, this one we're going to start with the ones digit. And very similar ideology to bucket sort, we're going to make 10 buckets, one for each digit, because that's how many possible variations of ones digits there could be. I think I just did this as one big animation. But here you can see there's 4 phases of scatter and then gather. So the way that this works is initially we will scatter based on the ones digit. So 2010 ends up in the 0 bucket. 7403 ends up in the 3 bucket. So we take a linear run across all of them and scatter them into these buckets. And then we take a k run, because k represents how many buckets we may have. So we loop k buckets across each items in the bucket, and we scatter them one more time, now based on the tens. And then we're going to do the same thing where we're going to gather and then scatter a third time based on the hundreds. And then we gather and scatter finally based on the thousands. And now, if you look over here, when we loop over, we're going to start at bucket 0 and we're going to loop 2,000, then 2,200, then 5,002, then 5,532. And so if we follow through this final orientation, this final gathering, that's where we're going to get a final sorted order for radix sort. Now, on the slide, radix sort looks really inefficient because we have to do this so many times. But the magic of radix sort is that each of these loops is sequential, not nested. So it's like we run over the data and then reproduce the data into some linear form. And then we run linearly over it and then we reproduce it. Linear, 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 all sequential. So, pardon me, right into the microphone for your enjoyment, Panopto. Can anyone tell me what is the worst case runtime of radix sort after all of these things? Yeah, it's linear, which is amazing. That's better than we could do with any of the other comparison sorts. So that is why radix, if you have something that has inherent sorted order, is the best we can do. Unfortunately, bucket sort, because it's got that insertion sort in the middle there, we can't guarantee a worst case runtime of linear. It depends on how k, the range of buckets, relates to the values of n. You can go read about that on the slides. Any questions about bucket or radix sort at this time? Okay. During the pandemic, it took so long for everyone to unmute themselves that I started picking up these weird little tics where I would like dance to like make sure that I waited for people to think about what questions they were going to ask. And it got weirder and weirder. And now I can't. We're in person. Okay. All right. Y'all, we are really close to the end of the quarter. You have done it. I know that this is not an easy class, but you are certainly over the hump. So exercise 5, the one about graphs, is due tomorrow. Tomorrow, we will release the exercise about sorting. And then a week from tomorrow, we will release the final exercise and your final assignment throughout the course, which will be, just FYI, it will be about all of the topics I'm discussing for these last 2 weeks of the quarter. And I'm not going to lie, it's like one of those things where I want to give you a heavy problem for your final programming assignment. So I got to give you like multiple weeks to work on it. And I want to do this whole resub thing for your final exam. So then I always end up with like 2 weeks of lecture time where there's like stuff that I know as a professional engineer is important for you to know, but I didn't have any class points associated with it. And I know how it goes. Like when teachers are like, okay, this isn't going to be on the test, but I swear it's important. Everybody poof vanishes. Understandable. So instead, we wrote exercise 7 to be what I will call conceptually less complex than the other exercises. It's entirely auto-graded, and it is my attempt to just give you brownie points for coming and listening to me be a windbag about stuff that I think is important for you to know. So intentionally, exercise 7 should be a lighter load. So really, I'm hoping that exercise 6 and the final resubmission are sort of your last like cognitively heavy things that you're going to do in this class. Of course, that doesn't feel great yet because the really intimidating thing is this Friday is our final exam. There is nothing during finals week. Don't come to whatever time is on my UW. Don't send me an email a week from today that's like, oh, I didn't come to the final because I thought it was during finals week. No, please don't do that. Please be here this Friday for your in-person half of the final exam. It will function just like the midterm. Bring all of the notes that you want. We will gather them, we will grade them, we will return them to you, and then you will have a chance to resubmit them for up to half of the points back. The TAs are leading an exam review this Wednesday, and I think that's Gowan, GWN, yeah, from 6 to 8:30. They also posted an extremely helpful list of practice finals and past exams and all that kind of stuff on the ed board to help you prep. Does anyone have any administrative questions at this time? Okay, see, I can't stop it. Now I've put it in my brain. I don't know, ADHD fidgets. Okay.
then let's wrap up this conversation on sorting, and we're going to pick up a new topic today. So, radix sort, I just wanted you to have a few, sort of examples here. There's an example walkthrough. Fun fact, radix, technically invented in 1890 by the US Census Department in order to sort. Lots of the wonderful things we do in this class predate computers, never forget. Oh, yeah, there you go. You walk through it, great. Let's talk about a sorting summary. Okay. Also, too, in your preparation for the final exam, hopefully you kind of know what to anticipate after taking the midterm, but if I was going to optimize my review time, I would go through all of the big topics in this class, like the big data structures and algorithms, and make sure that I know essentially this amount of data about it. Like, what's the best case that those things can run time in? What's the worst case runtime for any of those things? Do they use any extra memory? That kind of stuff. Because remember, what I'm going to ask of you on the final exam is, here's a scenario. What's the best tool for that scenario? If you use that tool for the scenario, what's the runtime? So make sure you can answer those level of questions. So I wanted to make sure we went over it from a sorting. Yeah, question? Thank you. Great clarifying question. So if you remember on the midterm, on the front page of the exam, I think we bolded it. It was like, you can assume hash table in practice runtime of O of 1. That's because there are times when like the theoretical worst case is just so statistically unlikely that if you were to say that to another engineer, they'd be like, the worst case runtime of a hash table is linear. That's ridiculous. And it's like, well, technically it's possible. That's when we distinguish for in practice. A good example is quicksort. If you say quicksort to the average engineer, they will assume a worst case runtime of n log n, because that's the in practice runtime. It could run in n squared. That is academically possible, but they don't live in the academic world. So I promise that if we have that kind of situation, make sure you read the front page of the exam, and we will bold and list for you. You can assume the in-practice runtime of this situation is, so that you can know what we mean there. Thank you. Good clarifying. Yes?
Unrelated to exam prep,
Sure.
do you happen to have a slide that summarizes all the algorithms with all the runtimes, all the best case,
I want to say I did at some point, and I'm trying to remember where it is. I will try to find it. Yeah, thank you. For the recording, the question was, do we have a slide that's like this for all the other algorithms and data structures? That would be a really helpful thing. I'm going to go find that. Future Casey, take care of that. Thank you. But let's talk about sorting here for a hot second. So remember that we first learned about selection and insertion sorts. Those are those in-place sorts where we're sort of shifting around in an array. Selection sort is that one where we look for what we sort of search through the unsorted list, we look for what we're trying to find, and then we swap things around. Insertion sort is as we're moving through, we find the thing and then we insert it where it's supposed to belong in the sorted list. So the problem is that selection sort has to run through its nested loops structure every time. So if your thing's already sorted, it's not going to run any faster for you. But selection sort can be stopped early if you only need the first 10 sorted items or something. Insertion sort will be optimized if you have a more sorted list. In fact, if your list is already sorted, insertion sort is smart enough to just do one linear pass through and like confirm that it's sorted. So that's a nice best case scenario. It also can be a stable sort. So it depends on your situation. Then we talked about heap sort. Heap sort also, like insertion sort, is smart enough that if you use Floyd's build heap, it's got a linear add. And then if your thing is already sorted, even though it's in heap order, which can happen, then it's just a linear run through. Otherwise, it has an n log n worst case runtime, and that n log n comes from the remove min percolate operations of heap sort. And there is a way to technically do it in place, but it is not a stable sort. There we go. You've got a few different distinctions there. Great. Merge sort is that one that I said is probably really popular, and in fact is one of the sorts that Java uses. Merge sort is not an in-place sort. Remember, it's got that recursive nature where it has to make new arrays of each of the halves, and then it recombines the halves. And so merge sort is guaranteed to always run n log n. And that's why it kind of tends to be popular, because engineers, we like predictability. We want to partition exactly how many machines. We want to know it's going to run in that amount of time. That's what makes merge sort really popular. Quick sort is, on average, faster than merge sort, but because the pivot is what dictates how you split the list at each level of the recursion, if you have a really bad pivot every single level, then you could have an n-squared runtime in Quick. So Quick can be a little bit faster, but it could also be a little slower. It's a little high risk, high reward, whereas merge sort's really that just like dependable kind of runtime. You can do Quick in place. And then we just reviewed bucket and radix. So because bucket does incorporate insertion sort within the buckets, if you say have one bucket that has n items in it, you don't know what's happening in your data list, right? That could happen. Running insertion sort on a bucket of n items could have a worst case scenario of n squared. So that's why that's there. But radix, thankfully, it tops out at linear. It doesn't have that unfortunate worst case scenario. Yeah, question.
Why does quicksort and in-place quicksort's best case not change, but like in-place for heap sort is slower?
So why are these ones? So this, because the heap sort, in order to accomplish the in-place nature of it, does this kind of weird swapping within the thing, you kind of destroy that linear just one wash through of it. So another great example of like trade-offs. It's really nice to save the space, but how likely are you to get that wonderful sorted order and runtime? And this is all based on the type of data you have. It's very common to have situations where your data remains in a mostly sorted order, and maybe you just resort it every time you add one new thing in. So if you have an already sorted list and you're just adding a new thing in, you have mostly sorted items and you're just inserting that one. That might be a scenario where you care about one of these ones that has a best case that's different than its worst case, as opposed to when you know you always have randomized sets of data, then maybe that's one where you want to get something that's predictable regardless of how sorted the original list is. I put some stuff in here about Java and what it does in particular, which I think is interesting. So Java technically leverages 3 separate sorts, all based on the scenario. And that's what we're really trying to take away from this algorithms unit, right? I know I just taught you a billion ways to do the same exact thing, but the point is, looking at all of this, that there really is no one singular best sort no matter the scenario. So the way that Java does it is, first of all, if what you are sorting is merge sort, or if what you are sorting is objects, it uses merge sort. Part of the reason for that is because whenever you're interacting with objects, you don't get that like coefficients boost from just using ints in an array. You got to jump around within the memory of the computer. So you already kind of lose the speed up that you naturally get from primitives. And also, whenever you're sorting objects, the chances is that that object might be sorted on one aspect, but not another one. And so that's usually where stability does matter. Like if you have a student or a human object, maybe you sort based on their last name, but you wouldn't sort on their first name or on their student number or something like that, so you still want to maintain relative order. So merge sort is what Java uses for objects because it's predictable, it's stable, and you don't benefit from any speedups if they are primitives. It uses something I didn't technically teach you if they are primitives. It uses dual pivot quicksort. So I showed you single pivot quicksort, but there is a version of quicksort where you pick 2 pivots, and instead of splitting it into like before pivot, pivot, and after pivot, you split it into like 5 sections, which is like before first pivot, between the 2 pivots, second pivot, after the second pivot. That's what Java does if you have primitives, because if you think about how quicksort works, especially the in-place one, there's a lot of just swapping around. And if you're swapping things around within an array and the array holds primitives, You get this great speed boost because the computer just stores all that data right there in the same location. So it doesn't have to follow arrows or anything like that. But just to make it delightfully more complicated, we always talk about these complexity classes as n tends towards infinity. Because the reality is that like we have big groups of data, that's what's happening out in the world. But even if you have something that runs in n squared time, what if all the constants and coefficients just make that thing execute so much more quickly at small values of n? And in fact, a bunch of wonderful researchers went out there and determined that if you have 48 or fewer primitives, that even though it runs an n squared complexity class, insertion sort is still the physically fastest, just because of the way the computer can handle things within an array. So if you call arrays.sort in Java, and it's objects in your array, it uses merge sort. If there are primitives in your array and your array is 48 or smaller, it runs insertion sort. If your array is 49 or bigger, it runs dual pivot quicksort. And this like delightful combination of things is essentially referred to as timsort. Timsort is also like a little optimization on merge sort. Any questions about how that all breaks down? Yeah, sure. What's the algorithm that decides which algorithms to use? So in this particular context, I'm talking about like the Java API behind the scenes of capital A arrays.sort. So that would be API that is now owned by Oracle, but once upon a time was created by Sun Microsystems. So.
But it does run some computation before it starts sorting. It doesn't just look at the field.
Yeah, it's literally like in whoever wrote the language of Java, I'm pretty sure this existed back when Sun used to own Java, because Java is also a thing that you can purchase. Oracle purchased them most recently, but they didn't write most of Java. Sun did. Sun wrote a thing where it's like, okay, if I call arrays.sort and I give you a parameter of an array, first it checks its type, and if it's an object type, sends you off to some, dot merge sort method. So there's some type of like logic within the original call to arrays.sort from the Java language. Yeah. Any other questions on sorting? Cool. Okay. Great. Yes, there are other cool things you can read. Here you go for it. But if you take nothing away, when somebody asks you what is the best runtime you can do for sorting algorithms, you will say for comparison sorts, it's n log n. That is the best we could do, unless you somehow find out a new sorting algorithm, and then someday I will teach your sorting algorithm to undergrads. I'm waiting for that day. I'll put your face on the slide. It'll be great. Okay, that's all I wanted to talk about as far as sorting goes. We're going to move into another topic now called dynamic programming. We're going to talk about it today and Wednesday. I somewhat recently added this to 373 because it is a algorithm optimization technique that has become more and more popular, and especially more and more popular in technical interviews, if that's something you're interested in. And I looked at all the non-majors courses and I was like, there's literally no other class that teaches it to you. So I guess it's me. Great. What is dynamic programming? It is just an algorithm, it's an algorithmic technique of optimizing how you calculate a solution by recognizing that the final solution is made up of previous calculations and being clever about how efficiently you can store those previous calculations or order those previous calculations. It makes most sense with an example. So let's talk about Fibonacci. Why are we obsessed with Fibonacci? I don't know. It just tends to be the canonical recursion example, and it works great for this. So remember that Fibonacci, any particular Fibonacci, is the product of the summation of the two previous Fibonaccis. Now, in dynamic programming headspace, right away, because the answer you're looking for is the result of two previous answers, that to you should send a sort of like red flag that this could be optimized. Now, because it's the result of two previous answers, it also might make you think this is a really good recursion solution. And that is true. Almost all the dynamic programmers, they start with a brute force method that is recursive. In the intro series, you learned something called recursive backtracking. Anything that's recursively backtracked, you can optimize with dynamic programming. So that's fine. I'll let you read through these. How do we approach this? So we could use recursion to solve the function. This is what the recursive method for Fibonacci looks like. It's got a base case. Otherwise, return the sum of 2 of the previous calls. Now, remember, when we do recursion, let's say we called Fibonacci of 5. What's going to happen is when it gets to this line, that's going to trigger 2 branches of method calls. 1 to a Fibonacci of 4 and 1 to a Fibonacci of 3. And then 4 will trigger 2 calls, and then 3, and so on and so forth. But each of those calls are unaware of each other. They're just triggered by that line in the recursive method, right? Now, if you look at this big bushy tree of recursive calls, can you see some redundancy? In fact, each of these things that I have highlighted here are us recalculating something we've already calculated. But because they're recursive calls, they don't have any awareness of each other. We're just like, you know, I kind of think of recursion as a robot. You just kind of put something in and the robot runs off and then comes back later. But once you've sort of like let loose of the robot, you can't really control until it gets down to base case and comes back up. So each of these recursive calls don't know about each other, which means each of these calls is unnecessary. So the core idea of dynamic programming is what can we do to prevent recalculating things that we don't need to recalculate. Here is, I think, the most elegantly simple part of dynamic programming. What if you just store them? What if you just make an array and you fill it up as you go, and then before you make any recursive calls, you just ask yourself, hey, have I already calculated that? If so, pull the answer out of this array and don't call that method. So you would have something called a memo. This is called memoization, not memorization, no R, memoization, and I'm going to mess that up at some point. The memo is an array where each of the indices represent the value of n, and the elements represent the result of calling n of that number. So Fibonacci of 0 is 0, Fibonacci of 1 is 1, Fibonacci of 2 is 1, Fibonacci of 3 is this 1 plus this 1 equals 2, Fibonacci of 4 is this 1 plus this 2 equals 3, so on and so forth. And so we add an if statement up here that's just like, hey, if whatever's currently stored in the memo shows that I have not calculated that yet, return that. Like just return the thing I already calculated before I get into the recursion. And in this case, because they're primitives, we had to like fill it up with -1s. But if they were objects, you would check if it's null. So it's exact, like if you look, this is the exact same code, except I check if I already calculated this before, so return the answer. And after I calculate things, I store it in the answer before I bail out. If you take nothing away about dynamic programming, this is it. If in an interview you find yourself recalculating things, commonly through recursion, add a memo, check if that thing has already been calculated, and make sure you store any new calculations. And I will be very impressed in an interview. Any questions on this piece? Yeah. What kind of situation would you use dynamic programming other than in an interview? Is that the question? Sorry, ask that one more time.
So I don't wonder, like, what kind of, like, for example, can you give an example, like, when we're going to use dynamic programming, rather than maybe just applying Fibonacci?
You can use this in any type of solution where you are asked to use previous solutions to calculate up to later solutions. I'm going to talk about Fibonacci and another one in this lecture. On Wednesday, one of our TAs is going to walk you through a bunch of other problems that are structured in this way too. For example, the knapsack problem, things like that. Okay, so at the very least, store your answers, don't recalculate them. But can we do better? Well, what if we also start to think about the order in which we calculate these things? Because in Fibonacci, technically, I only need like the 2 previous calls. So instead of creating a memo from the base case all the way up to what I'm doing, what if I make a memo that's just the most recent things I need and I cycle things throughout that, so at any given time, I'm only storing the exact amount of data that I need. And if you notice too, look, this actually eliminates recursion. So we started with a recursive problem, and it has a pretty naturally recursive pattern to it, but this is now an entirely iterative solution to Fibonacci. This is called tabulation. So instead of an entire memo that stores absolutely everything from your case down to the base case, it's just the immediacy of the cases that you need, and you sort of rotate your data through that limited amount of space. So we're even further optimizing the amount of extra storage space that we need. Now, this is, as you can see, based on sort of calculating in the order in which we need things. Sometimes your recursion, thinking about when you make your recursive calls, when you calculate them, can help you optimize for reducing recursive calls. Any questions on the tabulation solution? Yeah?
How are we saving space if we're still having like a new array with n+1 element?
So what we're going to do is here, we fill up the array initially, but then we jump in after that array. So it's like we kind of manually like start that instead of just like starting, all the way at 0 and calculating up. We're kind of like trying to eliminate some of those iterations by kind of preceding it there. But you're right, this does have an array of size n+1. And Casey just said, we only really need to keep the most recent things. Can we further reduce the storage space? Is this annoying? Can you tell where I'm heading with this? Aha, finally. Our most optimized solution, look, there's no array. There is just 3 variables. And this one is where we're just rotating through the variables, updating as we go. So this has the minimum amount of storage needed to still get us our answer. So it's sort of like as soon as we get the answer we need, we store it, we iterate around, we combine those 2 answers, and then we forget whatever that one is. We overwrite. So we're only ever using 3 variables in this context instead of an array. Fancy. Any questions? Yeah. So the term dynamic programming, which frankly is a terrible name because it sounds like nothing, is just this process of taking recursive, pre-computed solutions and summing them up to a final solution and reducing the amount of repetitive recombinations. That's what dynamic programming is. Dynamic programming, by definition, is an optimization technique where you're trying to reduce any unnecessary repeated calculations and then further trying to reduce any unnecessary storage. And specifically, the ways that you do that are what we would call memoization, tabulation, and then that bottoms up sort of directionality of it. We will do more examples. It'll make more sense as you get to see more examples. But since everybody seems to be so comfortable with it, why don't you try? You are climbing a staircase. It takes n steps to reach the top. Each time, you can either climb 1 or 2 steps. How many distinct ways can you climb to the top? Now, don't give me a singular way. Just tell me what is the permutation count of different ways for you to climb up a staircase, depending on whether you take 1 stair or 2 stairs at a time. Hint, the code I have shown you so far is dangerously similar to how to solve this problem. Dangerously similar to Fibonacci. Go ahead, take 3 minutes, discuss it with those around you, and then let's see if we can optimize. Start with trying to write a recursive one. Go ahead. All right, let's chat about it. So I told you it was dangerously similar to Fibonacci. And one thing to think about is how does the final solution you're looking for, the number of permutations of ways you can take n steps, how is that maybe the result of smaller problems or previous problems? Because we're in the dynamic programming unit, and that's how to think about it. Anybody have any ideas? Anyone want to describe maybe what they started to talk about together? Love to hear your thoughts on it. I know this one's complicated. Yeah, sure.
It's the sum of the solution for n minus 2 and n minus 1.
Yes, exactly. So, okay, ignore that. You can read all this in your own time. Here is, wait, didn't I? Okay, good, there we go. Here is the climb stairs recursive solution. I did nothing but change the name. It is Fibonacci because what it is if we can only take one step, we take one step. Otherwise, it's the combination or the summation of what if I take 2 steps or what if I take 1 step. So it is the final summation of the previous problems of what if my last step before the end was a double jump or a single stair step. Engineers love to do this in interviews. We love to take problems you've already seen and hide them in more ridiculous scenarios. I have no idea why we need to know the permutations of how to walk up some stairs, but somebody somewhere thought it was really clever. And this turns out to be one of the most popular interview questions. Hilarious. Yeah. That's a good question. I think in the clarifications, it's like if there's one step to take, you take that one step. And I think you're probably right, this n equals 0's base case, maybe that needs to go away. But I did pull this directly from the LeetCode code solution. So I think there was probably more in those slides that I skipped over about clarifying what to do in the base case. So if this is our recursion solution, can anyone tell me what's a way that we could dynamically program this to optimize it? What would we do? Any suggestions? It's the same code I showed you before. So can anyone remember how I optimized the code before? Anyone? Yeah, in the back. Yes. Sorry, say it one more time. Return Fibonacci. Maybe we've already done Fibonacci. We can just return that number. Absolutely. What are some of the dynamic programming techniques that we could use to prevent us from unnecessarily calculating previous steps? How do we get away from this recursive solution towards a more iterative solution? Anyone remember those words? Yeah, sure. Memoization. Absolutely. There we go. There's our Ivysaur. Okay. Here is how we would memoize it, where we just sort of keep track. Hey, store the results in there. There you go. This uses a hash map as a memo. But if memoization is the first step, here is the tabulation where we do make, there we go, there's our tabulation. And we, instead of relying on the recursion where we just check before we recurse if the thing has already been calculated, well now we fill up the table starting from the base case, rolling our way up. So instead of relying on recursion to go out and return, we just make one table and we fill it up and we look at the previous indice for the answer that we need in order to calculate this one. So instead of waiting for a return from a recursive case, we're just filling it up based on the previous entries in the table. So these are essentially like in the recursive example, the returns on methods, but instead of doing that, we just calculated them from the bottom up. And the reason we call it bottom up is because in recursion, usually we start at n, and then I say n minus 1, n minus 2, until I get to n equals 0, and that's when the returns start, and the returns kind of bubble back up to the top. This is like, instead of starting at the top and reducing down to the base case and then waiting for the return, let's just start at the base case and calculate our way up. That's what we mean by this sort of bottoms-up approach. Just jump right to where we know we're going to start doing the calculations and fill up that table as we go. And then the final mega optimized solution is when we do that sort of rotating values through the variables so that we don't need to store anything for any moment longer than we need it. Any questions? Okay, come back on Wednesday. We're going to do other examples of dynamic programming, classic computer science problems. And good luck starting to study for the exam. I know you'll do great.